Thank you. Hello, everyone, and welcome to our talk. Thank you for joining us. My name is Mihail. I'm a senior data scientist at GetYourGuide.
And hi, I'm Theodore, a data science manager.
And today we'll talk about how our team adopted deep learning for ranking activities in our marketplace. So I'll start off with a bit of context about GetYourGuide and why ranking specifically is an important part of our marketplace. Then I'll briefly talk about the learning to rank framework and how we use that to build the machine learning that powers the ranking system for us. Then Theo will talk about the state of our ranking system roughly about a year and a half ago when we decided to embark on this journey. And what was the motivation there, as well as how we approach this migration, specifically with respect to experimentation and what were kind of some of the challenges and learnings along the way. And in the end, we'll wrap up with an overview of two of the kind of more successful A/B tests that worked for us. And we'll also include a deep dive into the model architecture and some key takeaways of the journey. So for those who don't know about us, about GetYourGuide, we are an online marketplace for discovering and booking travel experiences. We are a two-sided marketplace, so that means we have essentially two types of users. On one hand, we have the suppliers who are pretty much like small businesses, so who come to our platform to list their activities online. So think something like a walking tour operator in Prague, for example. And then on the other side, we have the travelers. These are people who are come to our platform to discover and book activities and things to do for their next trips. And today we have over 100,000 activities online and millions of people using our platform every day. So with that scale, matching the activities that we have in our platform to the travelers is very important, and that's where ranking can really help out. And as far as ranking goes, for us, it's a really two-step process. So on one hand, we have the retrieval. So this is all about fetching a pretty broad set of candidate search results that are then or will be displayed to the user. And we use pretty loose matching. So for example, if the activity is tagged to the location that the user is searching for, then that would be part of the retrieval. In this example, the user is looking for things to do in Barcelona, and we've retrieved just over 800 activities that are tagged to Barcelona. And then the second part of that two-step process is the actual ranking part. And this is all about optimizing the order of the retrieved candidate results to essentially maximize the relevance for that user. Because if we can do that really well, that means there's a higher chance that the user sees something that is interesting to them, and then that maximizes their chances of converting, finding something they like and booking. And as we know today, screen sizes can be pretty small with like mobile, for example, and user attention is also pretty valuable and can be limited. So this really means that the top positions are very important, and we kind of need to make sure that we're nailing down ranking. And there's many factors to consider when doing this. So for example, there's seasonal patterns that are specific for every location. Some types of activities might be popular in the winter, others might be more of a summer thing. The user might have different constraints, for example, based on the language that they speak. We also need to take account the historical performance of the activity. If we know an activity has performed really well historically, that probably means it's more relevant in general. And then each user is pretty unique. They all have their own unique interests. So while one user might be interested in kind of the architecture and museums in the destination, as shown here, another user might be more into nature and kind of outdoor activities. So somehow we also need to take that into account. So how do we then make sense of all of this and make sure that we show the most relevant things possible? And yeah, for the last better part of a decade, I would say, the learning to rank framework has kind of risen as the de facto way of solving this task of ranking using machine learning. And it essentially boils down to using historical historical search queries from real users to then determine which items were relevant for that user, and then train a new machine learning model on that data. So as users come to our platform and interact with our marketplace, they submit a search query, maybe some filters to go along with that, and then we, the ranking service, we return a set of activities to display them on a given landing page. And as users view these landing pages, they also tend to interact with the contents shown there. So these would be the actual activities that they see. And by interacting, we mean really like clicking on things, viewing things, reading descriptions, maybe reading reviews, and hopefully even booking something. And as these interactions happen for each user, they generate events that we logged into our data warehouse. So, and it is these user actions, the clicks and the bookings, for example, that then determine sort of retroactively what ended up being relevant to that user. So then we process those events, we join the historical search queries that the visitors submitted with the subsequent events that they performed, or the actions that they performed, and aggregate those events, train a machine learning model, publish it to a model registry where it can then be picked up by the ranking service to be then used to serve new requests. And we complete this loop every day because, after all, user interests and preferences, activities, they change all the time. So we need to make sure that we're kind of up to date with, as up to date as possible. And this general workflow of using kind of real historical user queries with their subsequent actions as implicit feedback from the user is called learning to rank. And that's what we operate, that's what we use to train the machine learning models. Next, I'll pass it on to Theo to talk a bit more about the machine learning model and the stack that we use and what motivated us to move towards deep learning.
Great. So with that, let's dive into the model. So as you can see on the top, we are just focusing on this machine learning model part. And in there, what we receive is a query with a list of activities, and then we need to combine them first with some activity features that we retrieve from an in-memory database. And also we get some information from the traveler history from our feature store. And all of it will go through this scikit-learn pipeline, which will first pre-process the features using transformers on Panda data frame, and then predict using the XGBoost and XGBoost ranker, so using the learning to rank that Mihail talked about just before. And now what we are focusing on is basically just changing this model from XGBoost to a deep learning, and then we decide we move to PyTorch. So with that, you might be asking, but actually, why do we want to move to deep learning? First, we saw diminishing return on our tree-based approach. Indeed, we felt that we were reaching kind of the limits of what was possible with the current framework. Second, we saw much more flexibility with deep learning, in particular around model architecture, being able to customize the loss. It's also much better suited to exploit bigger data set. And finally, it's able to process in better way features like categorical features, or also being able to blend text, images, etc. And finally, and probably the most important, we also saw from external validation that other marketplaces like Airbnb, Wayfair, Etsy also moved to deep learning, and they all claimed that it was transformative in their approach to deep learning, to ranking. So in a nutshell, we thought we just go deep learning, we throw GPUs at it, and actually it was a bit more complicated. A bit more seriously. Sorry, I saw some people that wanted to make a picture of it. So a bit more seriously, by looking at other companies, blog posts, and also talking with some people in our network, we expected a long and complex process. And indeed, in reality, that was true. It took more than 6 months to do this migration. We also had some doubt around the infrastructure, especially the training time. We expected that to be longer. And yes, indeed, it took us longer. So for that, we had to tweak our CI. We also were not sure about GPUs. It was actually easy to train on GPU. But we had some hurdle when we had to train on multiple GPUs. Then on the inference latency also, we had some things that we needed to tweak into the parameters, into the setnum threads, etc. And then, yeah, what's the thing that we're the most afraid of is what is not written in the blog post, what are the things, or the thing that will be unique to us, basically. And actually, we got one of those. So the Docker image actually just blew up in size when we started installing PyTorch. I mean, we never told us about that, and we never think of it. But actually, then we had some CI running out of memory issues. So yeah, that's what happened. So now that I explained a bit more why we wanted to move deep learning and the challenges, I will show you how we break down this this migration into major milestones. So first thing that we had at the beginning of last year in Q2, we say that we wanted to first get to technical parity between our tree-based and our deep learning model. And for that, we just mean that we were able to handle the throughput with our latency requirements. And we started with a minimal hackable network. Well, with that, we spent 2 days focusing in the team, pairing together, and the goal was just to have some kind of hacky neural network, just 4 features instead of the 40 that we have for our tree-based. But at the end of these 2 days, we were able to have it deployed behind the feature toggle, but still in production, and we could already start testing with it. After that, we got into a minimal viable network, so a basic architecture, but with all the features. And we had some kind of okay-ish ranking metrics, but it was not optimized yet for all the business goals, but still we wanted to see the technical parity. So we launched an A/B test, mainly for learning purposes. By A/B test, what we mean is that actually for 50% of the visitors, they were exposed to the deep learning model, while the other half, so the other 50%, were still exposed to the tree base. And then we can measure the performance, like the interaction and business impact for these 2 parts. So based on that, then we finally launched the minimal level network. So what we get there is we have the same business objective parity, so that completed our technical requirements, and that's how we achieve our first milestone for the end of Q2. So with that, happy to take the question at the end, if that's okay. We move to Q3, where we aim to move toward business parity. Same as so what we want to have is the same business performance as our tree base. And so that in there, we start experimenting with new architecture, and especially with a transformer using self-attention. So that was the transformer, and we saw actually big improvement in our ranking metrics. We tested it in A/B test, and actually what we saw is that we had more people bouncing on our website, meaning more people that just opened the website, looked at the page, but actually clicked, got back to it without clicking on anything. So we then iterated and we moved to the click-based transformer. So we reuse the same architecture, but actually to account for this bouncing, we added the data of a visitor who also clicked on some activity, not just the people who booked activities. And there we were actually able to remove this bouncing difference between the model and got by that flat business result. And that's how we achieve our second milestone. With that, we were happy and we're moving to our last milestone. Now we wanted to outperform our 3 base. And actually, it took us 4 more iterations before we get our first win. And the first one that we get was actually the category converser transformer. So still using the same architecture, but what we added was a semantic similarity between the activity and the category on the page. And we saw an uplift in our ranking metrics, but also more importantly, we saw an uplift in the number of bookings. And that was just before Christmas. That was a kind of a nice gift for us. And maybe to make it a bit more visual, what we had is that we had a language model that compute the semantic distance between the category, and here the category for us is a croissant, baguette, and pastry. For us, category is a very broad name. And then we compare that with the activity test, and we compute then from this vector, we can compute the distance, or more technically consign similarity, and this is added as a feature to the model. Then in Q1, we had then our biggest win from the last years, and then we went deeper into the architecture and went to a new modern one with the deep and cross architecture, where we also had the trainable embeddings, and we also increased the size of the data set, and we got a clear win in our ranking metrics, but also in our business impact. Now with that, I will get back to Mihail. We'll talk a bit more about the architecture of the model.
All right. So yeah, at this point you might wonder, okay, so how does it actually look like, the model itself? And here's a little diagram. And yeah, to kind of start breaking it down, there's essentially 2 main components that go into into this model. So the first one kind of highlighted here is the deep and cross network, followed by the ranking transformer at the top. We'll go to that in a second. But it all starts down here with the embedding layer, where we essentially transform sparse features into dense representations. So for us, a sparse feature could be any categorical feature. So things like the user's selected language could be like one categorical that we consider sparse in this case. But it can also be any ID, so any specific identifier of an entity. And an entity for us is the actual activity or the location that we are considering when ranking. So we're generating embeddings for unique identity, unique activities and locations. So yeah, and then once the embeddings are created, they are actually concatenated to our dense features, which are things like essentially numerical features, things like the historical performance of the activity that I mentioned. That would be a dense feature. So we take this concatenated vector and pass it along to 2 parallel subnetworks. On the left here, we have the deep network, which is kind of your standard fully connected network with some nonlinear activations. In this case, it's the rectified linear unit. And the task of this subnetwork is to generate higher dimensional nonlinear features for the individual activities in a given query. And then on the right, we have the second subnetwork, which is called the cross network. And the task of the cross network is actually to apply explicit linear feature crossings. So traditional fully connected networks with nonlinearities are not very good at modeling these kind of explicit feature interactions, or the feature crossings as we call them. So for example, a feature crossing would be in our case, if an activity's category is pub tour and the user selected location is Prague, then the crossing is the Boolean AND, essentially. So normal neural networks are not typically very good at this sort of thing, but that's what the cross network takes care of. And then after these two subnetworks, the outputs are concatenated again and passed along to the ranking transformer, which is the second sort of main component. And here it is. So obviously, this is very heavily inspired by the Attention is All You Need paper. So that's the original paper that introduced the architecture of the transformer. So in our case, this our ranking transformer consists of two encoder blocks, which each have a three-headed self-attention mechanism, followed by a feed-forward network and some skip connections and layer norms in between, so kind of more or less standard stuff. One thing that's kind of unique is there's no positional encoding, so in kind of language tasks, the position of a token or a word is very kind of relevant because that really matters. In our case, the position only matters after the output, so we don't care so much about the position of the candidates before they are ranked. So that's why we don't really need the positional encoding part. And yeah, at the end we have the final layer, which is just a simple linear layer that returns the kind of relevance score, and we use that to then order or rank the activities in a query. And the task of this transformer is to essentially look at the full context of the query, so that all of the activities included in the query or the search results, and then apply self-attention to that, so that we can take the full context into account. So, for instance, if we have 5 other walking tours in Prague, maybe the 6th one is not as relevant. So that's kind of the what the self-attention there does. And so that's that. And I'll pass it back to Theo to talk about the key takeaways.
Great. So yeah. So first thing that I think is important is for us that we start simple to be able to learn fast. So we reuse as much as possible from the XGBoost model from the start. So we use the same data set, the same preprocessing pipeline, and then we tested incremental change offline and online. And that's how we tested more than 50 iterations and also launched more than 10 A/B tests, is by testing as small things as possible and see if it makes any impact. And that allows you to learn quickly. Then second thing is that we break it down in milestones. So we did first technical parity, then business parity, then business improvements. First, that allows us to celebrate in the team the achievement every time we hit a milestone, but also help us a lot to show progress to stakeholders to, yes, we are on track to deliver business result, but this quarter the goal was to just get technical parity. Finally, you can prepare and learn from others, but be ready to get some bumps on the road. For example, the people bouncing was something that we did not predict, but that informed our next step, so stay agile. With that, I think that's I think we're just 2 presenting, but it has not been possible with the rest of the team. So especially Nikhil, Jui, Olivia, and Xingting, who are not here, but also made tremendous things here. Thank you, and happy for questions. And we are hiring, of course.
Thanks for some vacation vibe. Who's got any questions?
Thanks very much. As someone without a machine learning background, but made some ranking algorithms, I found that super interesting. I was wondering about the event logging. I didn't quite understand where the event logging comes in, and whether the latest things that a user did have much more weight than the previous things they did, whether recency is taken into account.
So just to make sure I understand the question is like, do we, like something from 1 year ago, is it as relevant on something that's the last days? Is it the main question?
Yeah, you do things drop off the back as well, I guess.
Yeah, so basically what we do is so to answer to this is we retrain constantly our model so that we have the latest data and the model trained on the latest days of data basically. And so we go sometime in the back. At the moment we just train on around 3 weeks of data, so we're still pretty much constant in the things. We haven't put any kind of things in place to really try to diminish the importance as we go lower. Like the last week of the 3 weeks might be less important than the first week in a way.
What if somebody didn't do anything in the last 3 weeks?
No, in the queries, like from the booking that 3 weeks that happened 3 weeks ago might be still out of the seasonality compared to the things that happened in the last weeks. That's what I mean. But we don't train on visitor thing. We just how to say it. Not sure if I made it clear.
I think I was thinking it was personalized per person and that you're getting the user ID, and that's one of the features that goes in.
Okay. No, we don't use user ID as a feature because there are just too many of them, and I mean, most people don't have enough to train on things. But what we have as from the user, we can know what do they click on in the past, what do they book, etc. And this signal is then extracted and used as a feature. So we don't know your visitor, but we know that you click on X, Y, and Z, and this is an input to the model.
So this might be kind of a naive question, but how exactly did you come up with the architecture? And what I also mean by that, how sensitive is the model to small changes in the architecture? For example, you said we have this rectified linear unit in the neural network, and then maybe if I use some other type of activation function, how much would this lead to changes in the final result?
No, that's a good, very good question. So I think there's kind of two answers here. I mean, the first part is like literature, so we really leaned into that, what other people were doing, and kind of what were the more recent developments in the field. So I mean, none of this stuff we really like necessarily. It's not like our invention, like this. Where is it? The network architectures themselves. I mean, deep and cross is something I believe developed by Google like a few years back. And then obviously the transformer is very well known. So there's the literature part, and then there's the second answer is a lot of experimentation. So we're constantly like experimenting and kind of seeing what works and what doesn't. I would say in regards to your question, how sensitive it is to small changes, I would say probably not that sensitive. So if we take, I don't know, let's say the layer size of the deep network, the middle layer is 256, and if we change that to 512, it's not going to have like a huge impact, is what we've seen. But I mean, everything is kind of within reason. And obviously we kind of have to like guess a bit, so we can't possibly test all of the combinations. So yeah, it's a mix of leaning into the literature, testing a lot, and kind of, that's it.
I'm curious, to what extent is explainability an issue that you're interested in? And I'm coming particularly from the angle that showing relevant experiences is one part of the puzzle, but I think perhaps helping the vendors make their experiences more appealing by kind of doing something like search engine optimization for their storefront on your website, that could be informed, I guess, by explainability in the model to see what kind of attributes of a listing lead to more engagement. Is that something that you looked at that's interesting for you?
Yeah, no, I think it's a super interesting question. I think the short answer is we don't really consider that much in ranking specifically. I mean, we have other parts of the business, other teams who look into like search engine optimization and how to, give good guidelines for our suppliers on how to, what kind of pictures are good and bad and such, That's a completely separate thing. But as far as ranking goes, that's not kind of the main goal. We really try to improve relevance, and that's something that we can really measure based on historical data, so we see if we're making improvements or not, and that's it. I think explainability is kind of pretty secondary. I don't know if you want to add anything to that.
I mean, I think the way we approach it is we break it down in two. Is we say, okay, figure out how to make your activity as appealing and as many people book it, and then ranking will make it sure it will show in the right place. As better it is, the higher it will be your ranking and more impression you will get. So that's, I think, the way how we handle this discussion.
So we encourage you to keep discussing on Discord in case you have more questions. But for now, let's give a huge thanks for presenters.